So, let us continue our discussion on emulsion that we have been having. So, in fact, just to recap, what we did was we had an overview of asphalt emulsion, what it contains, what is an oil in water, water in oil, oil in water in oil. Then we talked about different classification system, cationic, anionic, emulsions, rapid setting, slow setting, emulsions. And then we also talked about the emulsion manufacturing procedure. Then we talked about little bit about emulsion breakdown. Okay, now if you recollect, I mentioned that this emulsion breakdown is slightly different depending on whether the emulsion breaks down in the presence of aggregate particles or without the presence of aggregate particles. So, we introduced flocculation and then coalescence, all those things. Then we went a little bit into the chemistry of the emulsifier. So, what is the pH level that you should have for a cationic emulsion, anionic emulsion, what is the dosages that you basically follow, and then in fact, if you recollect, this is where we stopped. Yeah. So, this is the typical emulsion recipes that we were really looking at. So, I summarized these two things, CRS, cationic rapid setting, similarly anionic rapid setting. What really is the difference? This is the difference, and what is the difference here? This is the difference, the pH that you are really looking at. So, this is what really makes, and what is the difference between rapid setting and slow setting? Basically depends on how much is the dosage that you have and what is the percentage of binder that you have got. Okay. So, now let us talk little bit about how the emulsion breaking process happens in the presence of aggregate, and in fact, we are very careful here. We are talking in terms of what is really called as the emulsion setting process. The idea is very simple. You need to take an bituminous binder, make it into an emulsion so that it can flow at room temperature, but that is just not enough. It has to break, it has to cover all the aggregate particle surfaces, and then it has to expel the water and function in the manner in which you envisage. So, your emulsified asphalt should revert to a, what is most important is the continuous binder film in order to actually act as a binder for the road material. Okay. So, the simplest sequences that we saw, for instance, flocculation, coalescence, and this results in the removal of water. So, this is something that we discussed, but there are different mechanisms that are at play as far as the emulsion setting is concerned. First and foremost thing is when you introduce the aggregates. Okay. Now, these aggregates can start absorbing the water, and then there will be some amount of evaporation also will take place, and this will be one important factor related to emulsion breaking. Second is there could be chemical reaction between the aggregates and the emulsion. For instance, if the net surface charge of one aggregate is of negative, and then if you are using a cationic emulsion, there is going to be immediate attraction. Your electrostatic, the potential that you need, you break it, there is no repulsion, and immediately there is a breakage that is going to happen. In addition to that, temperature, humidity, wind speed, and the mechanical action of basically trying to lay this material in the field. Let us say if you are talking in terms of the cold mix, these things also make a major role here. And then if you are going to have a less viscous asphalt, it is expected to have some kind of a faster coalescence, and it is not actually necessary for all the water for the curing to take place. And incidentally, you see that we are using the word curing. So, you need to understand the context with which we are using this word curing, okay, and it might take sometimes 3 months also. So, which means if you use a cold mix, the actual strength development will take 3 months, sometimes even 6 months also. So, let us say you are doing a road construction, you are recycling the material and then you are providing a cold mix with the emulsion, and then you start your construction of the regular hot mix material on top of it, and for the bottom portion which is the base course material, to gain its strength, let us say if you have assumed 200 MPa as the modulus value, to reach its actual strength it might actually take 3 to 4 months, and that is something that we just need to keep it in our mind when we are designing our pavement. And the strength of the reaction. So, these are all basically some of the important factors related to the emulsion breaking. Okay. So, the manner in which the cationic emulsion and the anionic emulsion are going to break are going to be completely different. So, if your surface net charge of the aggregate that you see is negative, then what can really happen? And let us say if you are going to have cationic emulsion, and you can actually see the charges here, net positive. So, two mechanisms are going to happen. There is going to be an immediate attraction, and in addition there is also going to be loss of water. So, when these two things happen, there is going to be emulsion breaking that is going to really happen. So, this is as far as the cationic. Now, what about anionic emulsion? Okay. The net charges are negative here and it is the same aggregate, negative. So, the only way in which the emulsion can actually break is by loss of water by evaporation, otherwise it will not really happen. So, why? You have a negatively charged drops of asphalt to negatively charged surface. So, these are some of the things that will happen. So, you are talking about anionic emulsion. So, the net charge that you see is negative, it is the same aggregate. In the earlier case, what is that you said? It was a cationic emulsion and it is the same aggregate. And incidentally, I have come across many instances in which many of my former students who are highway engineers at different places. So, they will just call me and say that sir, we did this cold mix or we did this, and even after 2-3 days the manner in which a highway engineer will speak is the color remains brown. So, it has not become black and it is like a mud, it is a slush. Okay. So, what would have actually happened? The emulsion would not have broken down at all. And incidentally, some of my students who are engineers in northeast, where the temperature is considerably lower and there is no evaporation that can happen. See, because if you see these cases, the breaking, emulsion breaking can happen only through evaporation, and if it is not really happening, then what can happen? You are going to see that emulsion remain as it is without any breaking. Okay. So, this is something that we need to seriously understand. So, that means you should have some idea about the type of aggregate that you use, whether that aggregate, what is the net charge of the aggregate, and whether you should, depending on that, you should pick your emulsion, whether you want a cationic emulsion or an anionic emulsion, and also factor the environmental condition. And again, you can go to the opposite. Let us say you are trying to do this kind of a cold mix in a very, very hot place, then the emulsion breaking can be sufficiently rapid, and that is something that also you do not want. So, that means you are looking at breaking the emulsion in the manner in which you want, and also you also want to monitor the strength increase, the rate at which the strength should increase also should happen in a very, very specific way. Okay. So, another brief picture, very simple picture for the emulsion setting process. So, how does this happen actually in terms of the interaction between the emulsion and the aggregate surface? The earlier explanation that I gave was fairly straightforward. What is the charge of the aggregate, what is the type of emulsion that you use, whether it is going to be attraction and expulsion of water or whether it is going to be just evaporation of water. Now, let us take a little bit closer look at it. So, the first and foremost thing is the contact of the emulsion with the aggregate. The second portion that you see is the free emulsifier that you see here. It is adsorbed and immediately the pH of the system rises, and when the pH rises there is some kind of a flocculation that happens, and after that the aggregate basically depending on whether you are using it for a prime or for some maintenance or a proper cold mix, the surface mineral surface area is going to get nicely coated by the aggregate. So, let us look at each of this in a stepwise fashion. Since this is very important, and since you may have access to the study material related to this or may not have access. So, I have just put these items in a bullet point so that you can actually go through this and understand how it works. So, now this free emulsifier that you have in your system, it gets adsorbs onto the oppositely charged mineral surface. Okay, please remember that oppositely charged, and this becomes lipophilic, and we have discussed what is lipophilic in the earlier slide. Now, the minerals, okay, the aggregate minerals will basically neutralize the acid in the emulsion, and this will lead to loss of charge on the emulsion droplet, and that will lead to first the flocculation, and then what is very important is the slower coalescence. We will talk about the rate at which this coalescence can happen as we go along. Then what will happen? So, now you are separating things out. The water gets absorbed by the minerals as well as it evaporates from the system, and the droplet that is in contact with the mineral will spread on the surface, and especially on the surface that is made lipophilic, eventually push out the water film on the aggregate surface. So, this is the important thing that happens. Okay. Now, to summarize, flocculation is the more rapid process, the coalescence that happens is a slower process. Number 1, the coalescence is an inversion process. Why it is an inversion process? Because the droplets that you see here, now you initially made your emulsion and breaking into small droplets and then covering them with the surfactant and suspend it in water. Now, in the coalescence what happens? The opposite of it actually happen. So, that is what is really meant as the inversion process, and the binder ratio of the it will increase. See, for instance, let us say you made an emulsion with 65 to 35. So, slowly it becomes 70-30 and eventually becoming something like 95 to 5. So, this is the proportion that I am talking about. So, 95, and now this remaining residual water will take some time for it to leave the system, and that is when the strength development also will take place little more slowly, and this is related to the curing that is happening in the field. And now, there is something interesting that I really want to tell you here. On one side, and this is something that you need to really carefully think about it. On one side, we basically say when we talk about moisture damage, and then formation of potholes, etc. What is that? We say we have this aggregate, and let us say it is coated with asphalt like this, okay, nicely coated with asphalt, and water, okay. What the water does? It kind of penetrates through this, breaks this film, and because the aggregate has more affinity to water than to the binder, and that is why what you really see is, you see that you have exposed surfaces, the film is peeled off, and then slowly one after the other the stone starts coming in, and you have your pothole and you have failure due to moisture damage, which is what we tried to simulate in the laboratory by making a sample, saturating it with water, doing a freeze-thaw experiment, then taking it to the room temperature, conditioning at 60 degrees centigrade, and trying to measure the indirect tensile strength. Okay, I am sure you may know most of these things. What is really called as the tensile strength ratio. Now, what is really happening here? The same water which was attracted to the aggregate particles in a regular HMA gets repelled in an emulsion. So, that means now you take an aggregate system of aggregates, mix it with the emulsion which is having, let us say, 65 to 35, and nicely the water starts flowing out of the system. Okay, this is really amazing, and in fact, in well constructed and well cured cold mix layers, you can actually see that the water is slowly seeping away and going out. Okay. Now, later during service, the same water can try to enter because of its affinity to the aggregate particle. Now, why this is happening? Think about it. This is something, a very interesting problem, and if you are unable to find an answer, drop me a line. Okay. Now, what exactly is the role of aggregates? Flocculation of emulsion droplets with the fine. So, this is how basically it starts really happening, because when you are mixing it, you have fine dust particle, and this flocculation, basically this emulsion droplet with the fines, you get kind of a nice mastic kind of a thing that you get here. Some aggregates such as carbonates and cement can actually neutralize the acid in cationic emulsion, and immediately the pH will rise. And in fact, one simple experiment that I do in my laboratory is to just take an cationic emulsion and add some cement and ask the students to stir it, and within few seconds you can actually see that the emulsion break completely, because immediately the system's pH increases. It goes from, let us say, 1.5 or 2 all the way up to 5 or 6, and then you basically see that in the glass rod that you use, this emulsion, the bitumen residue as well as the cement will cling to it, and you will see that there is a water. I will show you some interesting pictures as we go along. Two extreme cases happen as far as the emulsion breaking happen. What are those extreme cases? First is charge on the emulsion droplets is quickly destroyed by the pH changes. The moment the pH goes from 2 to 4 or 5, the emulsion quickly will flocculate and coalescence begins. Okay. Then second is, so this is the chemical part. This is, I would call it as the mechanical part, wherein you take the aggregates, gradation of aggregate, mix it with the emulsion and kind of do all this mechanical action. So, there is a loss of water and results in the droplets getting close to each other. So, that is what will really happen. Okay. Now, there are many theories that are available for modeling this system, the whole thing, and in fact, there is no one satisfactory procedure model that is available to explain this whole thing, but I am just going to show you something very interesting. Okay. So, another view of emulsion breaking. So, let us say this is your emulsion. There are two things that you are going to see. One is what is really called as film forming, another is what is really called as gel contraction, right. If you are going to go in this direction, what I want you to focus your attention is on the non-reactive aggregates. Okay. So, that means these aggregates do not really react with the emulsion. So, what will really happen? The only way in which the emulsion can break is through evaporation kinetics. See, when I use the word kinetics, what I really mean is a rate equation or something that is time dependent, that is what I am talking about. So, the film formation really happens. Another is you have a reactive aggregate. When it becomes the reactive aggregate, then what immediately happen? These emulsion droplets that you see here starts gelling. I think this is the most important word. Gelling happens, and when gelling happens, you can actually see how these droplets start doing, and what now happens, if you had evaporation kinetics, you are going to have what is really called as the contraction kinetics, and then slowly the gel starts contracting. So, this is the view of it. So, let me just quickly summarize these keywords here. Okay. So, if you are talking about the film forming, water evaporation and the droplet retains their identity up to high concentrations. Film forming, kinetics of film formation is influenced only by the evaporation rate, and the concentrated emulsion slowly start to have the final bitumen. So, in fact, what will really happen, as I said, 65 to 35 becomes 90 to 10, etc., etc. So, as it is being pushed close to each other, and you can, in fact, you can actually see here they are being just close to each other, the barrier has to break and the emulsion should start breaking, the flocculation and the coalescence should really happen. If I am talking about the gel contraction, and again I have put the keywords here so that it will be easy for you to follow: disappearance of electrostatic potential, and then rapid kinetics and formation of loose gel, okay, gel. And the characteristic time for the contraction kinetics is a function of bitumen viscosity, number 1, droplet size, number 2, and interfacial tension. Now, this bitumen viscosity is something that you can measure, you know it. Droplet size also could be estimated by, you know, particle size analyzer and all those things. The interfacial tension is very difficult to measure as far as the emulsions are concerned, okay. So, that is a different topic altogether. Maybe if when we do a course, NPTEL course on advanced material characterization techniques for bituminous material, we will talk about how to measure the surface charge of bitumen, surface charge of aggregate, and how they really do it. So, that is something that we will do it later, right. And gel contraction. So, change the pH to basically induce breaking, that is what it is. Now, here I just want to introduce a very slightly what you can say a detour that I am taking here. In fact, what is really called as viscous sintering. Now, this behavior is very fascinating, and we have demonstrated it also in our laboratory with one of our students, especially when you are having such kind of this behavior, this gel contraction behavior. Okay, so let us do the following very simple experiment, and in fact this was a paper that was published by these people, colloids and surfaces. You should, this is something that you should read it, and if you do not get a chance to get it, let me know, I will help you, right. Now, what is seen here in this picture is very smartly what these people did. They say these are all really fancy experiments, but people have been able to do it, and these experiments tells us lot of interesting things about what is really called as gel contraction. So, let us take a tweezer, a very small tweezer, and hold one droplet and another droplet here, and then try to kind of bring them together. So, you are going to have one droplet here, and then a slightly bigger droplet here, and when you try to force them together, it becomes something like this, and then slowly the surface starts contracting and it becomes like this, okay. So, now there are two important things here. The coalescence consists in the rupture. Now, we are not talking about flocculation, we have already reached the flocculation part. Now, we are talking about the coalescence. There is a small thin film. So, we rupture the thin film between the two adjacent droplets and through the nucleation of a small channel. The first nucleation step is followed by a shape relaxation driven by surface tension, which will basically cause the two droplets to fuse to a unique one, this one. So, they just come very close together, and then you get this dumbbell kind of a shape. Now, the interesting part is slowly due to surface tension it starts contracting and becomes the typical spherical shape. What will really happen, and these are events that are happening at different places in the emulsion. So, that means there is a nucleation step. So, that means this there are two droplets, this small interface that you see is forced out. So, they just join. So, let us take, you have a box full of emulsions, different droplets at different places. At any given time, you are going to see that there are going to be events related to the coalescence that is happening, and then, so let us say coalescence, call it as one event coalescence, and then once the coalescence happens between, let us say, two droplets, there is a shape relaxation that takes place. So, what will really happen if the time separating the two coalescence event is sufficiently large compared to the shape relaxation time? Now, this is the interesting point. If you are going to have a low viscous material, the time that is required to go from here to here is going to be very fast. Okay. Now, if the time that is required for this to form, this coalescence to form is sufficiently large, but once that happens, you are going to have considerably droplet size will keep on increasing. So, in fact, what will really happen? So, let us say if these two things together come together, and then immediately it becomes a sphere, because that the time associated with that shape relaxation is substantially small compared to the time associated with the coalescence. Okay, I hope it is clear. The next interesting part is what will really happen if the time that is separating the coalescence event is small compared to the shape relaxation. So, that means if coalescence is happening very fast, but the shape relaxation is taking sufficiently longer time. So, what happens is a gel is initially formed made out of irreversibly connected droplets, which is what I mentioned here. You get a gel. So, in fact, if you see this picture, the coalescence is happening fast. Ultimately, what would you expect? You will expect all this wiggly droplets joined together at some place to slowly get this shape relaxation done and become one single size, right, one sphere or whatever it is. That is what you expect to happen. So, a gel is initially formed made out of this irreversibly connected droplet, and the gel slowly continuously contracts in order to reduce its surface area. That is what will really happen. And what is very important as far as this particular material is concerned is, when a destabilizing agent is added to the initially stable emulsion, it forms a gel which contracts with the time by preserving the geometry of the container. This is really mind blowing. Okay. So, what it means, let us take an emulsion here, cationic emulsion. So, what you do is you add anionic. So, what you do, you chemically break it. So, when you chemically break it, what happens? The gel immediately, coalescence happens really fast, but the shape relaxation is not happening that fast. So, what will really happen is the material will kind of try to remember what was its original shape. See, because here it was a cylinder, okay, and now it also becomes something like a cylindrical block, and you can actually see how it is there. Normally, what we will expect? We would expect that it will become a sphere, because that is where, for any given unit volume, this is where you are going to have your minimum surface area, because that is what we know as surface tension. That is what will really happen. That will not happen here. Okay, this is extremely important, and in fact, this is the work done by one of our student. Her name is Adira. So, what she did was, I said let us try and see, check it out in our lab. So, she just take emulsion. So, you can actually see that she took the emulsion and added NaOH for 0.5 molar volume 20 ml, and after 10 hours, 1 day, 2 day, 5 days, 10 days, you can actually see how slowly the water is separating and a thin disc is formed, but still the water is unclear, the soap solution is present. This is for SS1 and SS2 emulsion. Now, you go back and recollect what exactly is the manner in which the slow setting emulsions are designed. The slow setting emulsions normally takes time and they are basically designed to break only due to water loss. Okay. Now, what she did was, she did the same thing with one RS emulsion, and as you add it within 10 hours, you can actually see, compare these two things. Within 10 hours, you can actually see how the shape has changed, and finally, we could actually take out the disc, if it was as a cylindrical disc from the water, and this is a clean water. You could check the pH, and then you could also check the pH of it. This is still a soap solution, but it has broken, but this is a clean water. Okay. So, this is what is really called as viscous sintering. Now, why should you worry about viscous sintering? So, when you are using this emulsion in a practical application, you need to really understand what exactly is the type of emulsion that you are using, what exactly is the type of aggregate that you are using, whether these charges really do match or not. Now, if I am going to have such kind of emulsion breaking here, when there is a gelling that is happening, the manner in which the emulsion is breaking is completely out of control, it is not in your control. Whereas, in this case, the manner in which the emulsion is breaking is in your control. So, it all depends on where exactly you want to use your emulsion. You want to use it as a prime, you want to use it as a tack, you want to use it in any of this maintenance techniques, fog seal, slurry seal, chip seal and all those things, or do you want to use it in your cold mix, that do you really want to use with wrap, because the wrap is coated with already with bitumen and you do not know what exactly is the surface, what was the original aggregate that was used. So, in all these applications you need to know. Why? Sometimes you can actually go to the field, get your reclaimed asphalt pavement, pulverize the material, add it with emulsion, mix it with emulsion and store it like a stock, and the emulsion will actually start breaking slowly during the construction process. So, you want the emulsion breaking to happen in a systematic and specific way, but when you are trying to do it in this particular fashion, what I have given here is, you basically do not seem to have any control, and what normally one can hypothetically say here is, you may not really be able to get the complete coating that you really want, but these things needs to be investigated and proven, but hypothetically one can say such kind of things here. So, to summarize the emulsion breaking summary, so the gel contraction as well as the film forming, similarly something to do with adhesion. Okay. So, if it is going to be a reactive aggregate, what exactly will happen? Type of aggregate, type of emulsion and other mixed components. So, in terms of emulsion, and if you are talking about film forming, this is going to be only in terms of the water content, water evaporation rate, because that is very important here, that is one, the slowly the breaking is going to happen. So, this in a nutshell gives you clearly what are the factors that will play a critical role during the emulsion breaking. So, let us continue our discussion about the emulsion test procedures, but before we do that, let us recap what are all the summary of the test procedure. One is the quality control, another is the shipping and storage, third is for application, and fourth is for identification. Okay. So, plant quality control, shipping and storage, application as well as identification. Now, let us just have a small recap of the emulsion production process, because we just need to keep it here. And here what I did this time, here I also tried to add some numbers to it as well as the temperatures here. So, the binder is roughly kept somewhere between 110 to 130 degree centigrade. The soap solution, basically water, acid and the surfactant in the order of this temperature 40 to 45 degree centigrade, and then you get a soap solution here. The pH now becomes, keep it at around 1.8 to 2. You can keep this temperature around roughly 60 degree centigrade. Now, this material is now non-Newtonian. So, when it is non-Newtonian, you know what I mean, shear stress to shear rate. So, it is going to be a shear thinning material. So, this is what your binder is going to be. So, run it in the colloidal mill and the emulsion, and at the same time mix it here. So, roughly this 130 degree centigrade and this is going to be 60 degree centigrade. So, let us take this as 40%, let us take this as 60%, and then the outlet temperature is roughly of the order of around less than 90 degree centigrade, 95 degree centigrade. Typically what you do after you make the emulsion, store it at 65 degree centigrade for 12 to 15 hours before you pack it and send it to the site. So, this is the same production process that we have discussed earlier, except that I just added few numbers here. Okay. So, how is the order of the emulsion, the solution here? Emulsifier first, additives next, acids or bases. Okay, number 1, you need to check the pH of the solution. So, this is about the plant quality control. Blend the proper amount of asphalt and check it, and what we really need is, this is the viscosity that we really want. So, in fact, what you really need to do is this concept of what is really called as the equi-viscous temperature. So, that means you do not really care about the temperature. What you really want to do is, okay, I do not really worry about the temperature, just give me a binder which is having a viscosity of 200 centipoise. So, you could get it at 120 degree centigrade, you could get it at 140 degree centigrade. So, that is what we really call as equi-viscous temperature, and in fact, in our course earlier also we have, when we talked about the mixing and compaction temperatures for bituminous binders and mixtures, we were talking about the equi-viscous temperature. Now comes the most critical thing. If you are not very careful, for instance, if you are not very careful, what will really happen? If the emulsion exit temperature goes above 100 degree centigrade and you have 40% of it is volume. So, one needs to be very careful, and there is a minimum emulsion exit temperature, it is roughly of the order of 20,000 centipoise. So, two important things, what is the equi-viscous temperature, what is the emulsion exit temperature. Okay. So, if we just draw a graph of so let us say we talk about a PG binder and another polymer modified asphalt binder. So, let me show it here. So, this is a PMB binder and let us say this is a regular PG unmodified binder, and so this is in temperature here, and this is the viscosity that you are really looking at. So, you can actually draw what is the line here, what is the EVT, emulsion exit temperature, in fact what is EVT here and what is meet here. Okay. So, if it is a PG 6722, we can think of it like in Indian parlance, we will let us think of it like a PG30 binder. So, this is what you are going to get, 177 degree centigrade. Okay. Now, so that means this is the graph that you have got. So, how do we get this graph? You just try to measure the viscosity of it as a function of temperature, and you basically get what exactly is the temperature. And in fact, what I did is, since this is from a US report, it is written in Fahrenheit. So, I just converted into centigrade and I have written here, and this is a 4% modified asphalt. The meat is 118 degrees centigrade and EVT is 218 degrees centigrade. So, this becomes very tricky. So, if you really want to make a polymer modified emulsion, I will not get into the details related to polymer modified emulsion. So, if the meat is greater than 95 degrees centigrade, then what we really need to do, we cannot really produce it under normal conditions, we need to produce it under pressure. So, you now know the school PV is equal to RT kind of a relation. So, recollect that. Now, another important point that we really need to mention here is, what about the, when I am trying to produce emulsion under pressure, what will really happen to the viscosity of the binder under pressure, because that is a very important topic. Okay. Will the emulsion viscosity will increase when it is produced under pressure? Obviously, because what will really happen when the pressure is increased, right, the viscosity changes substantially. This is something that is drawn in the log scale. So, you may not really appreciate it, but if you look at 60 degrees centigrade, if under normal conditions 0 pressure, if the viscosity is, let us say, of the order of 200, and if you take it to, let us say, 400 bar or something, it can go 5 times, the viscosity can increase 5 times, and this is for one grade of bitumen. So, let us say 60-70 bitumen, or you can think of it like a VG10 VG30 bitumen, you can think of this like a VG10 bitumen, and when you are using this bitumen of this particular order, the Newtonian viscosity, what you see here is it can also change. So, depending on the type of bitumen that you use, and when you are trying to produce your emulsion under pressure, the viscosity will shoot up now. So, then if you recollect, Professor Padmareka talked about time temperature superposition principle. Now, you relate it with that, there is also time temperature pressure superposition principle, those things are also available. So, the field will become very crazy if you start talking about all those things. So, we will not do that. Okay. So, you can actually look at it. So, for a meat of, let us say, 118 degrees centigrade, approximately you need to provide, let us say, 1.3 bars to get your emulsion at that particular temperature. So, this is the mill back pressure that you really need to understand. So, this is as far as the plant quality control is happen. So, what about shipping and storage? You need to check for storage stability as well as settlement at 24 hours and 5 days. What about the temperature for shipping? Okay, will there be a constraint? No constraint. And now comes the most critical thing. How do we really pump this material? Because you need to really pump this material if it has to be used in an application. Now, if that pumping operation can actually, it is a mechanical action, right, you are pushing it. So, what can happen? The emulsion can break. So, normally we use a gear type of pump, and only then it will be useful here. And identification, how do we really identify it? Can it through a spare nozzle? So, what we do, we just sieve it through a sieve and then find out to see whether it can, because during the prime application or tack application or any spray application, we need to ensure that this droplets, let us say you are talking about a 20 micron or a 30 micron, whether it can nicely flow through it. So, we typically take a sieve and then sieve through it and find out how much it is. You can go very fancy and try to do with the particle sieve size analyzer, and then try to check whether it is a cationic emulsion or an anionic emulsion, and the demulsifiability test, you try to add a salt and try to chemically break it. In fact, my suggestion is go check IS 8887 2018. There are a series of specifications that are written, there are test methods are also beautifully written. Okay. Kindly go through it. Again, if you are having trouble in getting the standard for academic purpose, I can share it with you if you send me an email. Okay. So, this kind of brings us to the end of the discussion that we started on emulsion. Okay. As I mentioned earlier, in the earlier editions of this course, we did not talk much about emulsion, but then later I felt that if I am talking about mechanical characterization of bituminous material, I need to actually add something about the emulsion technology, right. I just want to state one statement, read one statement from the summary of the emulsion state of the art as of now in 2007, it is still valid even after 15 years. In fact, what it says is the following: the hot mix asphalt industry has accepted that measuring the rheological properties of asphalt binders tell something about their performance. We have seen this throughout this course, your PGE, your MSCR and all that thing. Therefore, many of the traditional tests have been abandoned as specifications for asphalt binders. Okay, we have left it. But as far as the emulsion is concerned, it is still the volumetric flow rate based viscosity measurements are still being made. There have been some attempt to perform rheological tests, but the main problem is because of the recovery procedure used. Now, what exactly is this recovery procedure? Now, just think a little bit carefully of based on the contents that you have been listening in this course. What is the test that you do to mimic the changes that happens to the binder in hot mix asphalt? You do a short term aging, you do a long term aging to find out what is the status of the binder after 7 to 8 years of service life, right. So, in RTFO what you do, you more or less subject the binder to the changes that will happen to it during the mixing and compaction. So, the binder that you get in your lab after RTFO in a sense resembles the binder that is available in the field after the rolling operation is completed, right. But what about the emulsion? We have an emulsion, we mix it with aggregate particles, do a beautiful cold mix design, let us say with ramp, we lay it in the field, the emulsion breaks. Now, I would like to go take the emulsion residue and then test it, or to give a motivating factor, simple thing. Let us say you have a VG30, somebody says they have used a VG30 and made an emulsion out of it, and you would like to check whether it is indeed the VG30 there. Okay. So, you go take the mix from the field and then do the extraction, try to find out what is, whether it is VG30, but it will be very interesting, and that operation is very complex. Why it is very complex? Because it is not going to break immediately, it is going to take you months, sometimes even years also to for the emulsion to completely break. It will be interesting if you could develop a residue recovery procedure in the laboratory. So, that means you take an emulsion, do something in such a way that the water content is gone, and then you can actually find out, okay, so this is the bitumen that was used for making the emulsion, and so let me run some test on it. Now, the point is you need to do the emulsion residue recovery procedure in the laboratory in a way it resembles what happens in the field. It is very easy to actually take an emulsion, pour it in a tray, push it in a oven at 120 degrees centigrade, in no time the water is gone and you will be able to get the emulsion asphalt residue. But that is not really the residue that is actually available in the field, because this is a very slow process. There are many methods that are developed, and I did not want to get into it because I will be listing out a series of, okay, keep the oven temperature at this temperature for this many hours and take it out, and somebody else says no, keep the oven temperature at some other temperature. So, that is what really happens. What we do in our laboratory at IIT Madras, I just take a silicon mold, silicon tray, because silicon tray, it is very easy because you can peel the bitumen off. You pour it, let us say for half a centimeter thickness, that much material, just keep it under the ceiling fan. After 2 days or something like that, slowly after the water evaporates, you can actually peel off the bituminous film and then roll it, and you can do the testing. Now, is it the correct way of doing it? I do not know. It is one of the procedures that we have developed that we feel that is not very destructive to the material. Now, the bottom line is we yet are not in a position to actually find out a correct way of recovering what is really called as the residue recovery procedure. So, now the reason why we are not able to go forward as far as the emulsion testing is concerned is basically because of the acceptable residue recovery method. Okay. So, what really are the challenges? I will stop it here. As I mentioned, the emulsion residue recovery procedure, and then what about the PGF asphalt emulsion residue, and of course what about the rheology of asphalt emulsion. And the more important thing is, if I give you an emulsion and I want you to find out the viscosity, you need to be very careful about testing it, because what can really happen, the emulsion can actually break. Okay, so just need to be very careful. What about the shape relaxation versus flocculation? Of course, pressure dependent viscosity, and finally cold mix and wrap. Okay. So, with this I will conclude this lecture about emulsion. Thank you for your patient listening.